These are the learning targets that we'll be focusing on in this module, primarily how multiplication and division are related when developing conceptual understanding, and how to use different models and strategies for formalizing student understanding of these operations. When we looked at addition and subtraction, we learned about different problem types: joining, separating, comparing, part, whole. With multiplication and division, there are only 3 problem types. Take a moment here to pause and compare these 3 word problems. What is missing in each? Which are division and which are multiplication, and how do you know? And how might a student represent each problem? You probably noticed that the first problem is multiplication and fits with our problem type from the multiplication module. Groups times the members equals the total. The other 2 problems are both division, but they are looking for different things. In the second problem, we want to know how many cookies is in each group. So we do 15 divided by 3. This relates to the multiplication problem type, where we know the number of groups and the total, but we don't know how many in each group. The third is what we call measurement division, where we know the number in each group and the total, but not how many groups we're making. Read through the problem and then pause. How would you go about solving this problem? Here, Michaela knows the total number of oranges she has, 18, but she wants to put them in groups of 3. She doesn't know how many groups or bags that she has, so she has to figure out a way to solve for the unknown groups. It's important for students to make sense of the problem. Do they understand what they're looking for? Will they represent it as a division problem or a multiplication one? The expression we choose to represent a situation reflects our way of thinking about it and our reasoning of it. In other words, how we explain the situation guides the expression or equation we choose to generate for the problem. This is known as measurement division context. The student can find the number of bags by adding up by 3 oranges at a time, or by subtracting by 3s. One way to think about this is Halloween candy. 3 for you, 3 for you, 3 for you. We're going up as we're measuring out as we go. Pause here and read the problem. What are we trying to find out in this situation? Here, Michaela knows the total is 18 oranges, but she wants to fill up 6 bags equally. She does not know the number of objects, the oranges, which is the oranges, that go into each bag. This is called partitive division context, or sometimes called quotative. We are partitioning the oranges into the different bags, 1 orange in this bag, 1 orange in this bag, and so on, until we see that there are 3 oranges in each bag. Here are the contexts compared. Measurement division is counting the groups of objects you can make from the total. In partitive division, we deal out or partition the total number of groups of objects given to the number of groups. Teachers often say that division is repeated subtraction, but it only applies in one context, measurement division. Partitive division calls for a different strategy altogether, one in which the repeated subtraction is not easily seen. So just to recap, these are the different CGI, cognitively guided instruction problem types. You have joining with its subtypes, separating with its subtypes, part, whole, compare, and then multiplication and division. Let's go into a little more detail on these 2 problem types. Measurement division, also known as quotative division, we know the total. The number of groups is unknown. For example, we might have a container of sugar and a 1/4 cup scoop, and we don't know how many groups of 1/4 we're going to make. Or another example is that we have a bag of marbles, and we're taking out 4 marbles at a time. We don't know how many groups of 4 marbles there are in the bag. The second one is partitive division. We can think of dealing out cards. I know I have 4 groups or 4 people to deal cards out to, but I don't know how many cards each person gets until I've dealt them all out. In a moment, you're going to have, you'll see some videos that will demonstrate these 2 concepts. Keep in mind that the next video, there's no audio, so no, there's nothing wrong.
Today I will be explaining partitive and quotative division. Partitive division is used when you know the number of groups you will end up with. You just need to split items into the groups you have. So this is when you know the total number of items you have and the number of groups you have, but you're figuring out how many items are in each group. So we're figuring out how many items are in each group. That is partitive. And then quotative division is used when you know the number of items each group will have. So when you know the total number of items you have and the total number of items going into each group, you are figuring out how many groups you will end up with. So to start, we are going to talk about partitive division, where we know the number of groups to split our items into, and we'll be figuring out how many items are in each group. So to begin, we are going to start with 5 groups and 15 yellow candies. How many candies will be in each group? So I'm going to be using paper plates as our groups. So I'm going to have 5 groups, 1, 2, 3, 4, 5. So there's our 5 groups. And I'm going to have 15 yellow candies. And I'm going to put these 15 candies into the 5 groups we have, and we're going to figure out how many are in each. So I'm going to put 1 candy in each group. 1. And then I'm going to put 2 in each group. And then I'm going to put 3 candies in each of my groups. And in the end, we can see that with my 15 candies evenly distributed into the 5 groups, we have 3 candies in each of our groups. Now I'm going to move on to a different example using crackers. So for the cracker example, we are going to have 12 crackers, and we know that we have 3 groups, and we need to figure out how many crackers will be in each group. So here are my 3 groups, 1, 2, 3, and I need to evenly distribute my 12 crackers into these 3 groups. So I'm going to start off by putting 1 cracker in each group, and I still have some left over, so I know I can make a second group. I have 2 items in each group, and then I'm going to put 3 items in each group, and then 4 in each group. So in the end, with my 12 crackers that I evenly distributed into our 3 groups, I can see that I have 4 crackers in for each group. So 4 crackers for our 3 groups. And then for our last example with partitive division, we're going to use 21 cheese sticks and 7 groups, and we need to figure out how many cheese sticks will go into each group. So I'm going to lay out my 7 groups, 1, 2, 3, 4, 5, 6, 7, and then here are my 21 cheese sticks, and I need to evenly distribute the cheese sticks into the 7 groups. So I'm going to start off by putting 1 cheese stick into each group. And I still have some cheese sticks left over, so I know I can do groups of 2 items for each of my groups. And I still have some cheese sticks, so I'm going to put another cheese stick in each of my groups. And I finished distributing all my cheese sticks. So now that we can see with our 21 cheese sticks and our 7 groups, we have 3 cheese sticks in each of our groups. So that is our 3 examples using partitive division, and now we are going to move on to quotative division. And remember, quotative division is when we know how many items are in each group, but we are figuring out how many groups we will end up with. So for our next example, we are going to be using 13 animal cookies. And we know that there will be 3 cookies in each group, so we need to figure out how many groups we will end up with. So I'm going to lay out here are my 13 animal cookies, and I know that I'll have 3 in each group, so here's my first group. I'm going to put 3 cookies in it, 1, 2, 3. I still have some left over, so I know I can make another group. So for my group 2, I have 3 cookies in there. 1, 2, 3. I still have some left over, so I know I can make a third group. 1, 2, 3. I still have some left over, so I can make a fourth group. 1, 2, 3. And then I have one little cookie that will not fit into these, so I'll have it out. So as we can see, we end up with 4 groups, and we have 1 cookie left over, and that 1 cookie left over is called a remainder. So with our 13 animal cookies, and 3 in each, we were able to make 4 groups with 1 left over. Now for our next example, we are going to use 24 chocolate chips. 24 chocolate chips, and we know that there are 4 chocolate chips in each group. So do you know how many groups with 4 chocolates each will have? So there are 24. So I'm going to start off with my first group and put 4 chocolate chips in it. 1, 2, 3, 4. I know I have some chocolate chips left over, so I can make a second group. 1, 2, 3, 4. I'm able to make a third group. 1, 2, 3, 4. I'm able to make a fourth group because there's still chocolate chips in there. 1, 2, 3, 4. I still have some chocolate chips left over, so I know that I can make a group of 5. 1, 2, 3, 4. And I still have some chocolate chips, so I'm going to make a sixth group. 1, 2, 3, 4. So in the end, we end up with 6 groups. So 1, 2, 3, 4, 5, 6. 6 groups with 4 chocolate chips in each of them. All right. And now for our last example, using quotative division, we are going to use noodles. So I'm going to have 20 noodles, and there are going to be 5 noodles in each group. So here are 20 noodles and 5 noodles in each. So I'm going to start off with my first group and put 5 noodles in it. 1, 2, 3, 4, 5. And now I'm going to make a second group with 5 noodles. 1, 2, 3, 4, 5. And I'm going to make a third group with 5 noodles in it. 1, 2, 3, 4, 5. And then I still have some noodles left over, so I know I can make another group. So this is my group 4. 1, 2, 3, 4, 5. So in the end, we end up with, after dividing the noodles up, we see that we have 5 noodles in our 4 groups. So I distributed our 20 noodles with 5 in each, and we have 4 groups. All right. So now that summed up our partitive and quotative division, and I just want to remind you that partitive and quotative division, what their definitions are. Partitive division is when we are figuring out how many items will be in each group, and quotative division is when we are figuring out how many groups we will end up with.
In the first video about baseballs, the student counts out the total number and then makes or measures out groups of 8 to figure out how many boxes she can fill. In the second context, she counts out the 20 cupcakes, but then she needs to show the 4 boxes and deals the cupcakes into the box one at a time. Then she counts how many cupcakes were in each box. What this shows is that for young students, the 2 different division problem types really impact the ways in which they solve problems. Take a moment to read through each problem and identify them as either a measurement problem, measurement division, partitive division, or as multiplication. You can check your answer when you hit play, but hit pause and do it. How did you do? Can you explain the difference between measurement and partitive division? Students in elementary school need to be exposed to these different problem types. Again, the point isn't for students to know about the problem types or name them, but rather for teachers to make sure students get experience with both types of problems. Beyond fourth grade, problem types can help us think about how to frame division with fractions or integers to make sense of them. Take a look at these four problems and think about how measurement or partitive division in each is helping students make sense of the problem. Pause here and take a moment to play with these ideas. For example, think about a third divided by 2. It is much easier to do with partitive division. 1/3 cup divided into 2 equal recipes would be 1/6 of a cup. When looking at 2 divided by a third, it's easier to think about how many thirds are there in 2, which is measurement division. Likewise, when students first start operating with integers, -6 divided by 2 is easier to think of with a partitive context, like dividing 6 negative ones into 2 jars would give us -3 in each. On the other hand, -6 by -2 divided by -2 is easier to think about with a measurement context, like how many groups of -2 can we make from -6? Having these two different ways to think about division can really help us make sense of division in different ways. Number strings and division problem types can really help us when developing our reasoning within division. For example, we can think of 6 divided by 2 as either 6 divided into 2 groups of 3, or how many groups of 2 are there in 6, which again is 3. We can use that to figure out the next problem. 6/10 divided by 2/10 is easiest to think about from a measurement perspective. How many 2/10 are there in 6/10? There are 3 groups of 2/10 in 6/10. How many 200ths are in 6/10? Well, there are 10 hundredths in 0.1. So the answer could be 10 times as large as the previous problem. Then I can use measurement division again here on the fourth one. How many 200ths are there in 600ths? Well, there's 3 200ths. But the last problem is easier to do with partitive division. What do I get if I divide 600 into 2 groups? I get 3 hundredths. One final thought. It's important to note that our students don't need to know or be able to identify these problem types, remember. It's more important for us, the teachers, to make sure that we're aware of what the kids are getting exposed to. We're going to move into how to formalize some of these division strategies. We're not going to jump straight into an algorithm. We have been using some visual and contextual strategies and modeling, and now we want to shift into some more formalized strategies by using and building upon what students know. How would a student who does not yet know how to use the long division algorithm complete each of these problems? Note that the numbers are all the same, but we're focusing on how the context or the situation in the word problem and how this might cause students to create certain pictures or use certain kinds of informal strategies. You'll want to pause here and sketch out your thoughts on how students might solve these problems. The candle factory problem has kind of a rate idea. We are looking at boxes of candles, each of which has 24 candles, and we need to get 768 candles. Students will sometimes just add a bunch of 24s until they get to the desired total of 768. From the multiplication module, we know this kind of strategy can be turned into a ratio table. Take a moment to compare these two ratio tables and how they reach the answer. Pause here to study and then press play when you're ready to move on. When we use ratio tables for division, our answer isn't in the total, but rather the number of boxes it takes to reach that total. The other strategy students will tend to use in these types of problems will be subtracting down, repeated subtraction. Maybe they take away one at a time, though with these numbers we hope they will think to take out larger groups. This kind of informal strategy relates well to what we call partial quotients. In this model, students think about how many groups of the divisor, 24, they can take from 768. So maybe we start with 10 groups of 24. That would take care of 240 candles. Let me grab my pencil here. I'm right here. That would take out 240 candles. We have a lot left still. So let's try 20 groups of 24. That would take out 480, which leaves 48 left. That would be 2 more groups of 24, or 2 more boxes. So we can make a total of 32 boxes of 24, and we get that 32 from right here. A note about partial quotients. We really do want to understand that we really want the students to understand that they are taking out groups from the total. This helps support the understanding of what division really is. And I also want to clarify the importance of using academic language here. This strategy is called partial quotients, not Lucky 7, not the box method, but partial quotients. The partitive division problem of dividing 768 pencils into 24 classrooms leads to different kinds of strategies. Rather than just adding or subtracting, people will tend to think about dealing out the same number of pencils in each classroom and then seeing how many pencils are left over. So if every classroom got 10 pencils, that would use up 240 pencils. We still have a lot left. So here's where we're at. Everybody gets 10 pencils. Let's give 20 pencils to every classroom. Okay, that leaves 48 pencils left per classroom. Adding up those, we've given 32 pencils to each classroom. So let me get my different color and we can look right here. There's our 32. Pause for a moment and see if you can see where that same idea is happening in the partial quotients example. Where do you see the 10 and the 20? Take note of the partial quotients take note of why the partial quotients is more efficient. Is the thinking different, or is it just that the representation or modeling is different? A partitive division strategy can also be used to derive our standard algorithm for long division. We're going to take a look at a different division problem, 768 divided by 3, to make this easier to model. We basically move from each place value to the next, trying to divide that place value into 3 equal groups, because our divisor is 3. Let's start with the hundreds and deal them into 3 equal groups. Each group would have 2 hundreds in it, and then there is 100 left over. We'll move that extra 100 into the tens column, so it now becomes 10 tens. Now there are a total of 16 tens. Partitioning those tens into 3 equal groups, we can put 5 tens into each group, but still have 1 10 left. Again, we'll move that 1 10 into the ones place as 10 ones. Now there are 18 ones. Each of the 3 equal groups gets 6 ones, and there are 0 ones left. If we had a remainder, we could continue to move down into decimal values. Although teachers love the area model for multiplication, we tend not to use it for division unless given a context about area. That said, I've talked to a number of teachers who say this model helped their students connect multiplication and division together visually. If we have a roll of carpet that's 768 square feet, and we know the width is 24 feet, we can find the length of it, starting with rolling out 10 feet, and then another 10 feet, and continuing on. On the next slide, or on the next bit, you'll see a model that represents this idea. We end up with something similar to an area model. Note that we could also have broken apart the 24 into a 20 and 4, especially if it had been an uglier number, meaning not friendly like tens. So let's take a minute and look at long division. Hit pause for a second and find the comparisons between and connections between the partial quotients and the traditional algorithm. Hit play when you're ready to resume. Long division is probably the most opaque of the traditional algorithms. We start by asking a question. Can 24 go into 7? You'd think we're really asking how many times 24 can go into 700. There's a lot, but that's not what we're asking because 24 can go into 700 at least 30 times. What we're really asking is how many whole hundreds of 24 can go into 700s or 700, because 100 24s is larger than 700. We say 0 right there. Moving on to the next place value, our question is how many whole tens of 24 go into 76 tens or 760? Well, there are 3 tens of 24 or 30 24s are in 760. We subtract the 72 tens to get 48 left over. Moving to the ones, how many 24s are in 48? 2. This conceptually is really difficult, but partial quotients can support students in understanding the traditional algorithm. We've been using the same numbers in each model to make it easier to connect between them, but we should point out that all these models are flexible. We've talked about flexibility with ratio tables, but partial quotients is also flexible. And while working in 25s may not be my go-to, there may be students who do. We also see that a student who does the 20 in 2 steps working in tens. There's a balancing between honoring students' thinking and pressing them to be more efficient. We shouldn't just jump to the most efficient method then because then they're dependent on how well they remember and not build on their understanding of equal groups. All of these methods were 3 steps or fewer and thus pretty efficient. They also don't require the guess and check multiplication we find on the side of student papers when doing long division. Sometimes I see this as a transition to the traditional algorithm, stacking up by place value. This is also useful for dividing when we want to go to a decimal and you can continue to build. We give students lots of tricks when it comes to memorizing the steps of standard algorithm for division. We acknowledge that these are given with the best of intention, trying to make math easy and fun, but these tricks do not support the understanding of division or the process or the development of number sense. They do support the notion that making sense of things doesn't work, so it's better simply to follow steps. Quick story, 4th grade student who was showing how to do long division. He could easily do something like 468 by 9, divided by 9. But when he asked what 468 divided by 19 was, he said, oh, we haven't learned to do this with 2 digits yet. Now let's think about it. That's really chilling. He had no strategy for figuring that out. Now, if you're not sure, all you would do is cut the quotient from 468 divided by 9. You'd cut that in half because your number of groups is doubling. He had no strategy for figuring this out, not repeated addition, not thinking about taking out groups, no connecting between 9 and 18 as the divisor. So the question becomes, did he even understand what division was? Rote algorithms are not bad. There may be times when division and number sense are not the point of what we are doing. And having an algorithm you can run through it is really helpful. Although with the advent of technology, that's becoming a little more dicey. But they don't support ideas like place value or number sense. They are in the standards, so we need to make sure students have strong foundation in those areas first. In the standards, we can see a progression. We'll start with multiplication and division with hundreds, then, or 100. Then we'll move to those informal methods we've talked about, adding up, subtracting down, chunking, or using number lines. Then we move to models that emphasize place value and number sense, like the partial quotient model, or area model, or even ratio table. Finally, in 6th grade, that is the first time kids are introduced to the standard algorithm for long division. We can see this progression as we go through the standards. Next, we're going to watch a video which is Graham Fletcher's division progression video. Take a look at these models. Spend some time exploring and connecting the mathematics. You can also find a copy of this in your pause and play document. Now that we've discussed some efficient computation methods, let's consider two kinds of activities that press students to reason about division. In this problem, think about how the context in word problems changes the way we use numbers. Pause here and think for a moment, what would be a word problem associated with the number sentence 78 divided by 8, where the answer is 9? Just do that first one and then press play to continue. For the first problem, you might have come up with something like this. I have 78 cookies. 8 cookies can fit in a bag. How many bags can I fill? Now, try the other 3. Here are some possible solutions. The first one, we knew we could only fill 9 bags. But to answer with 10, we might need to know how many bags to store all of the 78 cookies. In the first one, we could only fill 9 bags, but there were some cookies left over, so we would need another bag to store those. In the third one, we came up with 78 cookies shared equally between 8 people. So how many cookies, including the cookie fractions, would each person get? The last one, for the answer of 6, is an expansion of number 1. How many cookies are left over after I fill all the 9 bags with 8 cookies? We start talking about remainders. This is a reasoning problem that we're going to try mentally. Abe has 157 miles since the last time he filled up his gas tank. He fills his tank 9.54 gallons until when he stops to get gas. To calculate his gas mileage, he divides 157 miles by 10 gallons and finds the rate of 15.7 miles per gallon. Was his gas mileage better than 15.7 or worse than 15.7? How do you know? What we hope kids would realize is that if we're really dividing by a smaller number, 9.54, our 15.7 is an underestimate of the gas mileage. His gas mileage was actually better than 15.7. This is the kind of mental math that can help us focus on concepts of what division really is. Let's take a look at some of the takeaways from this division progression. We talked about different contexts, and as in all the modules, how the context drives the strategies that the kids use. We also looked into the multiplication division problem types of multiplication, measurement, and partitive division. We then looked at division concepts directly connected to the ways we operate with fractions, decimals, and algebraic expressions. This is an opportunity for coherence across the grade levels.